different type of relationship derived from the original one, and then a numerical transformation. In between the centrality, things get even more complicated. Between the centrality is supposed to measure how much control maybe someone has over communication flow in the network. If that is assumed to be along shortest path, then we can count the number of shortest paths that connect the source and the target, and the share of those that have I as an intermediary. And if I is an intermediary, then maybe I has control over the commutation going on. So we can take this as the dependency of a source and a target on an intermediate I, and summing up the dependencies of all the pairs on a particular node gives us the betweenness centrality. This is actually the smallest graph there is, for which closest degree in betweenness have different centers that are unique in the graph. Right? We didn't prove this, we just did this by enumeration. We enumerated all graphs with at most 10 nodes, and this is the unique smallest one that has this property. Right? There's some others that have similar properties, but that's about it. So these are the three prototypical centralities. There's one more that was left out in Freeman's article for strange reasons, I'd say. And that's eigenvector centrality, so feedback centrality, where the centrality of a node depends on the centrality of its neighbors. Okay, so how people try to, so there's not much about it, but at least there are some attempts of bringing order into this whole system. Basically in two classes. One of them is axiomatic. Starting even in the 60s, people come up with criteria, maybe properties that indices should fulfill, then prove that these criteria are independent, and then in the end usually prove that there's only one index satisfying all of the criteria that are there. Right? And the essential ones that are almost always present, or at least the basic idea that is underlying most of these axiomatic systems, is that the index should be invariant under isomorphisms, so we have graph invariant that is assigned to the nodes, and the second one is that it should be beneficial if edges are added. So if a vertex receives a new edge, or if an edge is switched from one neighbor to this particular vertex, then that vertex should always benefit from it, or at least it should never suffer. These are the two main things in these axiomatic systems. In the conceptual part, Borgatti and Everett tried to explain that maybe centralities can be divided into those that correspond to a particular flow process, some way of in which something in the network is being propagated, like information, like rumors, or maybe even goods or electricity, whatever the network is representing. That can be along different types of paths or walks in the graph, and it can be a different transfer process. Things might be copied, they might be split, they might be unique and then passed on, whatever. So these are conceptual ideas of what kind of process could be described. And then we could also look at whether the node in question, the one that we want to assess the centrality of, is at the beginning or receiving end of such a transition, or whether it's somewhere in between. So radial and medial classes of centrality indices could be distinguished. A bit problematic is that the axiomatic systems usually are designed to characterize a particular index. Right? So we're just gaining a different description. We're maybe learning something about the properties of this index. Usually we're not learning something about a class of indices. Whereas in the conceptual part, it's nice to be able to differentiate between the ideas that are underlying and maybe some of the mechanisms that have been used, but we're not really getting an index to compute. Right? Maybe we can classify some indices based on how they're designed, but that's dangerous because sometimes the mathematical definition has equivalent versions that correspond to a different type of process but ends up in the same numbers, and that we don't see here. Right? So even this top-down or this say specification implementation approach is not really giving us a good handle. It seems that the only thing that people agree on ever since Freeman wrote this explicitly is that if something is to be called a centrality index, it must assign the highest value possible to the center of the star. Right? This is the most centralized network, and the distinction between the center and the periphery should be the most clear. That's a very, very weak requirement that is satisfied by many things that if you look at it on a different type of graph, you would never call a centrality. But at least it's the one common basis. Maybe we're learning something from seeing how these things are being applied. Here's an example that I picked at random, biased by looking at things that are cited a lot. So this paper is very well received. It has some 5,000 citations in Google Scholar. And the way that the centrality is used is as an explanatory variable in some hypothesis testing. So the idea here is that we're looking at organizations. We want to understand what makes a business unit trustworthy, and a factor in this is supposed to be the centrality of that business unit in the social interactions that are taking place in the company. Right? So we have, as the explanatory variable, oops, let's go here. Right. As the explanatory variable, the centrality of the business unit in this network of social interactions, and we're comparing it to the level of trustworthiness, or the perceived trustworthiness that is assigned to this unit. So there's a questionnaire being handed out, people mark business units, how much they trust them on certain things. Maybe the question is less explicit, but it gives us scores of perceived trustworthiness of these parts of the organization. And on the other hand, we have the ranking of centralities, and if we compare these, they should align. That would be the hypothesis. Now the question is, in this hypothesis, it should be testable if it's an hypothesis. But in the hypothesis, we only say centrality. So we need to make a decision on what kind of centrality it is that is being used to test this hypothesis. And the authors of this paper, they choose between us. There's a long discussion on why social interaction, how trustworthiness is perceived, and so on. The discussion on the choice of the centrality index is rather short. It's this. So it's basically an argument by authority, where we see that Freeman argued that this is the most suitable in a very general setting. Right? So any kind of social structure, any kind of information access benefits, that's very general, not very convincing in my opinion. Also, the test is done via correlation. We have seen that between this gives us numbers, but we have also seen in closeness, for example, that the reversal was done by a hyperbolic transformation, so maybe these numbers are not necessarily linear scaled in the level of trustworthiness. So that seems to be a bit of a problem. To see what assumptions are being made by applying any of these centrality indices, I'm choosing closeness because it's a little bit easier and a little bit faster to explain where these hidden assumptions are that this choice entails. I mean, if I argue that someone said this is a good index, I should have an idea of what it's computing and what the assumptions are that I'm buying with this decision. So here's the definition again. We're looking at distances in terms of shortest path. So that's an influence model. We're already, by picking this index, we're already deciding on how information is spreading in the network. It's spreading along shortest path and shortest path only. And then only the distance matters, not the number, whatever. So that's the influence model we're buying with deciding on closeness. Then we're also making a homogeneity assumption. It doesn't really matter who the target is. If there's a specific t that I have a certain distance with and another t that I have another distance with, if I exchange the two and the distances are the same, the measure is not going to change. So that's a very strong assumption that all members of the network are being created equal. The third assumption is that those distances are additive. Right? Having twice a short distance is the same as having once a long distance. So we're measuring on an interval scale. And the third one is this particular functional form of the transformation, because the goal is really only to reverse the interpretation of having high total sums of distances as meaning low centrality. I could do this in another form, and of course that would affect something like the correlation score. Right? So with all these assumptions, so with the single decision to choose closeness, we're actually making a number of decisions, and none of them can easily be changed, or this is the reason why some variants have been invented. But the root cause of the problem is really not these individual decisions, but in my opinion, the root cause is that we want to make this a quantity. That we want to pretend that we can measure something in quantitative terms that represents the centrality of a node in the network. To me, that's the root cause of evil here, because it's this decision to have a quantity is the reason for the other three problems that we see here. The only thing that is really not affected by this decision yet is that there needs to be an influence model. But this influence model is where the theory should go, the kind of thing that we're measuring the meaning of the network that we're looking at. So I guess that's okay that we need to make this decision somewhere. For the others, there should at least be choices. Right? And maybe if these choices are not necessary, if they're only induced by the fact that we want to have a number then they're problematic. Different from other situations in empirical social research where indices are constructed for particular purposes. This is rarely the case for centralities. It's rarely the case that someone argues, I have this situation with these assumptions, with this theoretical background, I need this index. Rather, it's this selection of indices that are available, mostly in software, and then one of those available is being picked, right, and not questioned. So I think that's the main problem that we have. And as I said, I want to avoid this problem. I'm not going to solve it. And avoiding the problem is easy if I drop the assumption that I need to have a quantity. And now a spoiler alert, the next slide will have my pretend solution on this, and then I will explain why I think this is a partial solution. All right, so here's the spoiler. The idea is to set up the different criteria that to separate indices or any kind of analysis that correspond to centrality from others by making just one requirement, that whenever we have a node that has a few neighbors and another node that has at least the same neighbors and maybe more, then we can never rank this one below that one. Right? Having the same and more ties can never make you less central. This corresponds, of course, to the additional switching argument, but it's much simpler because it can be tested inside of the same graph. Slightly more mathematical. We're saying that the neighborhood of I, so the black vertices up here, if that's contained in the closed neighborhood of J, so the neighbors of J including J itself, right? Because otherwise we would not be modeling the edge in between the two. If that's the case, then whatever index or whatever kind of centrality we're doing should never rank I above J. That's it. It's like an action, but it's a different type of action because the actions in the axiomatic systems are based on numbers that are being assigned, whereas here it's just a requirement. So we need to preserve this dominance relation, and then we're fine. It can be done without looking at other graphs. It can be done inside of the single graph. It can be done without doing graph modifications, so we don't need to worry about maybe we want to design something for trees. In trees, we cannot add edges without creating cycles. So we're stuck somehow in the requirements that we can add to the construction of the index. We don't have that problem here. And of course, since we don't have numbers, really we don't have to worry about normalization and scaling and these other transformations. Okay. Why do we think this is a good criterion? Well, because it is shared by all the centrality indices that are currently being used, so it seems to be the joint idea that is behind them. So it might make a good basis as the one requirement that should be fulfilled, and it's in fact more general than the star property that Freeman had in the paper. And I will show you why this is the case. So let's look at shortest path distances again, the influence model underlying closeness. Shortest path distances are computed by looking at all possible paths that go from S to T, determining their length by summing up either the length of the edges or the number of the edges, so a uniform length of one. Summing these up, that gives us the length of a single path, and then if we have a number of alternative paths, we select the one that has the best value, so in this case, the minimum of the distances. If there's no path, then we just have infinity as marking the non-reachability of T from S. So we have as input a graph that contains edge weights, edge length as T. These are summed along any walk that leads from S to T, and then we pick out of those that connect S and T, we pick the one that has the minimum total sum. That's how shortest path distances are computed. But this is only one instance of a very general influence model if we abstract from the way that these two operators are defined. So if we turn this into what is called a semi-ring, so we only require not the specific operations, but some operations that fulfill certain requirements, in this case semi-rings. So we have certain values, in this case length, an additional operation that represents the aggregation of path, and a composition operation, the multiplication that represents the concatenation of path, and a 0 is the neutral element for addition, and a 1 is a neutral element for composition or concatenation. Then we can define in the very same way the structure is the same, but it gives us something other than shortest path distances. Right? If I use, say, the maximum and multiplication as these two operators, I get the most reliable path if the input values are probabilities. Or if you remember George Connor's talk on current flow is determined from Kirchhoff's laws, but that means that the concatenation is serial composition and the aggregation is parallel composition. Right? So many of these indirect relationships can be defined via semi-rings, and even more than you probably would imagine. And in fact, all of those that are used in current centrality indices can. So with this, we're actually removing the dependency on a particular influence model by just assuming that the observed network X is transformed into some tau of X that represents the indirect relationships, and then we get a new network that is valued by the values of tau. Okay. And in this new network, we have a monotonicity that is always satisfied if the semi-ring is plausible for the interpretation that is generally given to any of the centrality indices, namely that if you add an edge, so if you make a path longer, it is never helping, it is never decreasing the distance or increasing the connectivity. So we call this a decreasing semi-ring, and the simple requirement is that if we add an edge in the beginning, so if we concatenate to the solution that we have another edge, that's not improving the situation. Right? So farther away is always worse, or if it's about strength, then adding some weak tie is not strengthening the relationship. And then we can prove that if the semi-ring underlying the influence model is of this kind, then neighborhood inclusion implies that also these transformed values satisfy the same directional inequality. Which means that if we have a centrality index based on aggregation of such values, like closeness summing over all of the distances, or like degree summing over all of the direct neighbors, or like betweenness summing over all of the one-sided dependencies as a dependency relation, which is also representable as a decreasing semi-ring. Whenever we have this, that means that neighborhood inclusion implies monotonicity in these values, implies the same inequality for the centrality. So this relationship is shared by all centrality indices. Right? If we have this situation, then we have this ordering. And we can prove this in very general sense, even for eigenvector centrality, which may seem strange because it's usually thought of as a feedback centrality, but it can also be represented as the share of all walks of, or in the limit share of all walks of the same length originating at a particular vertex. So we have another concatenation and aggregation, namely summing operation here. That is nicely represented in generating function, but this is also the reason why I'm not explaining this in detail. Arvid Schoch and I have a paper under review, and this is explained. If you're interested in this, I'll be happy to send you the draft. Okay. So we have a property that is shared by all centrality indices that are out there today, at least all of those that we have looked at, and you can believe me that we looked at quite a few of them. And that has immediate consequences. So we can learn something about centrality in general just by applying this one single property. For example, we could be interested in graphs in which every pair of vertices is comparable. And in which, for every pair of vertices, we can say that one dominates the other. And that includes its neighborhood and maybe additional ones. There's a whole class of graphs called threshold graphs that is very interesting. It has a book and many articles about it that is defined in this way. So if neighborhood inclusion is complete, if every pair of vertices is comparable, then the graph is called the threshold graph. And stars are members of this class. So in a star, here the immediate ranking is shown by color. Of course, it has this vertex dominate all of the other ones. But there are more general graphs, like these examples here, in which every pair of vertices is comparable in this way. And for all of them, the ranking is fixed. Right? All centrality indices preserve neighborhood inclusion, or this dominance relationship. Because dominance is complete, there's no degree of freedom for the centrality indices. All of them will give the same ranking to the vertices of this graph. Right? On others, like the small example that is still in the lower right corner, they differ. But on these graphs, they do not. That has interesting consequences also for empirical networks. So with Tom Valenti, we're working on a paper redoing an analysis that he did a long time ago in empirical social networks, where they were looking at the correlation of centrality indices. So how similar are they, and can we learn something about their differences by looking at when, in which situations they do not correlate. And in this chart, what you see here is the distance measured in terms of graph modifications necessary from a threshold graph. So if the graph is close to a threshold graph, the social network that we're looking at is close to it, then it's far to the left. If it's very different from a threshold graph, it's far to the right. And this is the average correlation of the standard centrality indices on this graph. Right? So we have a bunch of graphs here, and you can easily tell that the closer they are to a threshold graph, the more the indices correlate. That's very clear. The farther they are away, the less these indices correlate. So they do show the differences, but the set on which the original paper was written of graphs is exactly this. So most of them are fairly highly correlated because most of them have this periphery kind of structure where some nodes dominate all of the other ones. So he's not really studying the differences between the indices, but he's studying a particular type, a particular class of graphs that are very common, core-periphery structures. And especially in empirical social networks, these appear quite a lot. And that has consequences also just for simple algorithmic tests. So if you design a new centrality index, you want to show that it is different on something, or you want to show how fast it computes and so on. Preferential attachment graphs are a bad test bed, because preferential attachment graphs are very close to stochastic threshold graphs. We're always selecting nodes that already have many neighbors, so we're creating dominance all the time by creating these graphs. So we have lots of predetermined orderings. We cannot find big distinctions because they will all give ranking or the highest ranking to the nodes that are early on the hubs in the network. Right, so be aware of the generators you're using to test these things, because this might be one of the reasons why you're not seeing anything. Right? The restriction to this class of graphs. All right, that's one thing that we learned from it. Another thing is that most graphs will not have these comparable pairs of vertices. Right? And if you just think of a cycle, every node on a cycle has one neighbor that the other neighbor does not have. So no two vertices are comparable. And that's true for many graphs. So even though it's a very clear shared criterion, it's one that isn't necessarily frequent in empirical data. Right? We have seen that maybe that's because the graph is only slightly off, but in general, especially with multi-centered graphs, we will be far away from a threshold graph. So we have almost no requirement on the centrality indices. That can also be a good thing, because then we're not excluding anything. But we'll be working on this in the second part of the presentation, where I leave you with all the additional problems that come about. Because I have not solved anything now, I only have shown you what the intersection of the current centrality indices is. This property of dominance is being preserved, but that may be too strong a requirement because it's almost never satisfied. Right? So we're now generalizing this. From this we have an implication that I will explain later on, and that will be the new requirement, the more general, the weaker requirement, but where we can put in a lot of substantive theory to explain why we want to have this. So we generalize this ordering into some other ordering as a prerequisite for centrality indices. But to do so, and because I was very irritated by yesterday's panel on computational social science, where there was this cockfight about who's owning the field, I wanted to insert a slide on what I think this field is and why no one's owning it, really. So to me, network science means that we start from some phenomenon, and that phenomenon is represented via abstraction in some conceptual idea that corresponds to a network. So there are objects, and these objects are linked. And that's the concept of a network, but that requires abstraction because we have to say what the objects are, what the relationships are, and so on. And then we represent this in data by having observations on the relationships. And we've already said what the objects are, but we don't have the data yet on the relationships, so that's where the data comes from. And a network model then includes both of these steps. So it includes the abstraction. If it includes the abstraction, you cannot go the reverse. You cannot find out something on the data and interpret it as a feature of the phenomenon, without going backwards in the abstraction. And the abstraction is always subject dependent. So we're not doing anything for all of those fields that are using network science in their applied settings if we're just telling them that we found out this and that's meaningful, if we're not making sure that it actually matches the abstraction that led to the result. So substantive theory is decisive to have meaningful results. And therefore, it is owned, well, at least this applied part of network science is owned by everyone. And then maybe we can distinguish two others, the pure, or if you like, abstract part of it, where we're looking at mathematical structures, general theorems, and so on, and the computational part, where we need to calculate indices, or do clusterings, or manage the data, or observe them. Okay. This view has one other implication that I think is very important. So if you don't want to remember anything of this talk, remember this line, a network is not the graph. A network is something else. A network is data. And it's data on dyads. So we have dyadic data relationships between pairs of objects, and whether we have data on all pairs or only on a subset of the pairs, or what pairs these are, it's a different matter. Right? We may represent this in the end as a graph, but the data that we have is data on dyads. Let me define notation for it that makes it more clear. We have a set of nodes, maybe affiliations, where affiliations might be something else, like people and organizations, but it might also be just the same people. Right? So affiliations can be the same as the nodes, which gives us then the one node network. The data that we have is defined on a domain that consists of pairs of nodes and affiliations, or nodes and nodes, if both are the same. And for all of these units of observation, we have some observation. And maybe there's a zero included or an infinity, depending on what we have. So some element that represents the absence of the relationship. But there's a difference between the absence of a relationship and not knowing whether one is there. So not having this dyad in the domain for which we have the data. Right? So this graph represents a one-node network, but we don't know whether this is a dyad that has a zero value or that has not been observed. And that's a big difference, for example, in sports networks where you have teams playing each other, but not every team plays every team, and so on. So I think that's the main difference here. The second thing is that now that we have this representation, we can take this either as a matrix or vector, or we can look at it as a mapping from the domain to the values. And I would like to represent this as a directed mapping from source to target for this particular relation with a particular value, because that is supposed to be general enough to cover all kinds of multi-layer networks with additional attributes and different types of relationships and so on. So every observation that we have consists of these four components, right? The type of relation, the value, and the involved nodes and affiliations. All right. You can express ego networks and everything else in this way. Leads us to generalizations, and that's modeling what Peter Blau proposed for social space, that elements, individuals of a social structure are characterized by some parameters, maybe their age and their years of education. So every point here is a person that is of a certain age and has a certain number of years of education. And the idea in Blau space is that this space, these individual attributes, correspond to social structure, that there is an association between the two. For example, in this picture we have the situation that marriages are mostly within a certain level of education and also mostly within a certain age band. So the attributes of the individuals are partially determining, or at least are associated with the relationships that we see. More importantly, the representation of the individual is by its position in this space. So the position of the person related to the attributes of the different dimensions. And I would like to generalize this to relational structures, to network structures. Balázs yesterday mentioned the position of the broker, right? And this kind of reference to the notion of position is very frequent for different types of position in different types of networks. So we can generalize this by looking at all the relationships, all the attributes that an individual is involved in. So the attributes would be something like the Blau space, but we add to it the relational dimensions where the dimensions itself are defined by the targets, the affiliations that define this relationship. So we have this very general setting, and now the network is gone. We don't need the network anymore because all of the network is in the indirect relationship and the dimensions that define it. So now we can do multivariate analysis if we like. So using this, we can generalize the pre-order condition very easily. So a node was dominated by another node if the neighborhood was included. In this positional setting, that's the same as saying that in the adjacency relationship X, we have that the position of I is dominated by the position of J if for all T, the relationship is at least that big. So if they both have no relationship is 0, then that's fine. If both have a relationship, both are 1, that's fine. If there is a difference between them, then it needs to be on this side, where the 1 is. So that's equivalent, of course, it's just a characteristic vector. Now we don't have to look at adjacency, we can take any transferred relationship, like distance, for example, and this gives us a requirement that is closer to what closer centrality is doing. In fact, we can also add homogeneity by saying that it doesn't have to be the relationship with the very same individual. So it's not like in Blau space where dimensions are labeled and labels cannot be changed, but we can exchange them. In this particular case, it means everyone can be replaced by everyone, and it's very interesting to use other permutations, other levels of homogeneity that can be introduced in the network. And finally, we don't even have to restrict ourselves to the value of the relationship, but we can also take into account who is in this relationship. Right? So for example, it might be a difference if you have shares of a company and that company is currently performing very well. So if I'm comparing my shares in one particular company with someone else's shares in another company, maybe I make these companies homogeneous because they're in the same sector, but maybe I don't want those shares to be compared directly because they represent other projected earnings, for example. Okay, so by considering this context, now we have a very general notion of when the position is better than another, but we can substantively explain why we think that this decision is necessary without resorting to numbers necessarily. Right. And just to finish this off, one example that is more pictorial so that I get rid of all the formulas. That's a classic data set on diffusion of innovation. It's physicians in 4 different places. They have or have not adopted a new drug. And the color, if they're colored, then the lightness of the color indicates the time at which they adopted the drug. The data set was collected very innovatively at the time by looking at prescription records in local pharmacies. So if someone prescribed a drug and the first time they did so was checked by looking at the pharmacies when there was a prescription record of that kind. Now the question that has always been asked is the position in the network of physicians in terms of advice relationships, friendship relationships, and discussing medical topics, is that associated with being an early adopter or not? So people who are close to many others in the profession, who are sought out by others in the profession, as maybe advice givers or people that you relate to, are under pressure to adopt an innovation that is consistent with the norm of the group early on. Right? So being close to others, being the target of relationships, should make you adopt earlier. That was measured, so this closeness to others was measured with actual closeness. There are various variants for disconnected graphs, but as you can see, they all somehow correlate, except that this hyperbolic transformation and the linear transformation here lead to slightly curved shapes for the different places. Right? Okay, so all of these values are essentially the same. Now the thing is that if we correlate this, or if we plot this against adoption date, then we should see a falling line. The less the distance, the earlier, so the higher the closeness, the earlier the adoption should be. This is adoption time, so we should have a falling line, less central, later adoption. These are the ones that for which adoption has not been seen. That correlation is significant, but it's very weak. Right? And some articles have been written that some index of centrality is a better predictor of adoption date than another, but as you can see, these differences are very small. Right? These are rank correlations here, because we don't really have to take these as numbers. And what we can do now is we look at positional dominance, as a requirement that needs to be satisfied by any centrality. So if I want to come up with a new centrality that performs better than the others, I would want to know how much better can I be, or are the ones that are there, are they doing a good job? However, if we do inhomogeneous domination by using the distance transform, we get very few comparable pairs, as I said before. So we're introducing, as all of these centrality indices do, homogeneity. Then all of a sudden, lots of pairs become incomparable. So of all the pairs in the different places, most of them are comparable. Some of them have the same value, and some of them are tied in terms of this dominance relationship. And what we see here is that the rank correlation of those that are comparable by anything that is monotonic in the distance is still very low. Right? And the best projection that we can have is if all of the incomparable pairs are made comparable in the right way according to the adoption date, which is, because they're interdependent, is a very positivistic upper bound, we still don't get out much except for this smallest place. So that's an argument that is general over all possible, even the ones that we don't even know at this time, centrality indices that are consistent with this idea of dominance, that they can never be much better than what's already there, and that maybe there is no centrality effect that is substantial in this situation. And this is indeed what has been shown in other studies, that other attributes are better predictors than this centrality idea that was there at the beginning. Okay, so in summary, this is what I think, how empirical network analysis should proceed. That we start by looking at what is observable, how does this give us the unobservable indirect relationships that we could otherwise have observed directly, when are nodes comparable, what makes relationships comparable, then this gives us a partial ranking, and if necessary, then we can aggregate the scores and the positions into something that is then used as a number later on. But in many cases it will not be necessary, and all of the difficulties that are associated with this step may be gone away. And I have now given you a recipe to create the next 1,000 centrality indices by just defining different types of positional dominance, taking into account different attributes over time, multi-layer, whatsoever. And if you take this framework on one of the previous slides, that gives you new centrality. And then there are lots of other open problems, but I leave you with the slide for the end. Thank you.